Welcome to Module 5, where we will be wrapping up Chapter 4, where we will finally touch on the stoichiometry that's been in the title of this chapter the whole time. All right, so before we actually get into the chemistry, we want to talk about an example and analogy. So suppose you want to make a sandwich. And so one sandwich has a recipe. It is made of 2 pieces of bread, 2 pieces of cheese, and 3 pieces of ham. So these are your input ingredients, and you need a count, you need a particular number of each of those ingredients to come together to make your sandwich. So we can see here would be all of my input ingredients and then all of my output sandwich. I can condense that representation by using some coefficients. So I can say put it 2 times the pieces of bread, 2 times the pieces of cheese, 3 times the pieces of ham. What I can then ask is I can start to think about, well, how many sandwiches can I make from a certain amount of ingredients that I have? We know that one sandwich is 2 pieces of bread, 2 pieces of cheese, 3 pieces of ham. Well, how many sandwiches can I make with 8 slices of cheese, right? I have some amount of ingredients. How many sandwiches can I make? Do I have enough for what I would need, for example? And how we can think about this relationship is as a unit conversion problem. And this may seem overly formal because it is, but we can think about it in this way. We know that based off the coefficients, there are 2 pieces of cheese for every 1 sandwich. And so what we are functionally doing is taking the 8 slices of cheese that we started with and dividing them by this 2 slices of cheese per sandwich, telling us that we will make 4 sandwiches. So these coefficients that are in the front of those numbers allow us to do conversions between amounts of product and reactant, or ingredients and output sandwiches. Right? These numbers that define the fact that you need 2 is defined by how we make sandwiches. It's defined by the process. And so that recipe governs how much you can make from a starting amount. Well, say I'm going to make those sandwiches. Say I have my 8 slices of cheese. I know I can make 4 sandwiches. Well, how many slices of ham would I want? Right? I know that I need all 3 of the ingredients in order to make this sandwich. So if I have a certain amount of cheese that I need to use, how much ham do I need to pull out, right? How much of that? And we can see that we can still use those coefficients. The 2 slices of cheese is 2 slices of cheese. Let's switch to green. The 3 pieces of ham is the 3 pieces of ham. So we know what this tells us is that for every 2 pieces of cheese, we will need 3 pieces of ham. So because I have 8 divided by the 2 gives me 4, and then 4 times 3 gives me 12. So I can see that overall, I'm going to need 12 slices of ham. So I can relate amounts of ingredients using the recipe as well, right? You would do this if 1 cake calls for 2 eggs. If you want 2 cakes, you need 4 eggs. Right? And so you can use these ratios to inform the relationships between these different amounts of things, which is really what we want to be able to do. How many sandwiches can we make with 12 dozen slices of cheese? Now, I'm not counting individual pieces of cheese. I'm counting by groups. I'm counting by the dozen. So I have 12 dozen. And so what I can see is that the 12 dozen is still related to the number of sandwiches using the same coefficients. It's still the 2 and the 1 that's implied out here. But the thing that we note is instead everything has the exact same dozen. Just like we've seen previously, you just don't change the counting unit. Those ratios stay the same. So those coefficients apply when you're working in counting units or when you're working on individual pieces of cheese, individual pieces of ham. They all still come together. But you'll note it has to be the exact same counting unit everywhere. So if you're going to use dozens, it needs to be dozens everywhere. Reams, gross, anything like that. Pairs, right? 2 pairs of cheese. You'll need 2 pairs of cheese for every 1 pair of sandwiches. So it's tied to chemistry. Stoichiometry is the quantitative relationship expressed by coefficients of your balanced chemical equation. So instead of talking about making sandwiches, we could say that you need 1 molecule of C3H8 to react with exactly 5 molecules of O2, right? The one's implied right there. And if you do that, you will make exactly 3 molecules of CO2 and 4 molecules of water. What that means is for every 1 molecule of propane, you need 5 molecules of O2. And you will get 3 molecules of CO2 and 4 molecules of water. The idea and the goal of stoichiometry is to answer those questions that we were asking with the sandwich example. If I have a certain amount of propane, C3H8, that I start with, how much CO2 will I get? Okay, that's a really, when we do chemical reactions, we generally are concerned with how much stuff are you making? And that's a really fundamental question. Another common question would be, I want to make a certain amount of water. I want a certain amount of product. How much reactant do I need to put in? Because that means how much right? If I have a goal for how much product I want to make, or I figured out how much of that first reactant I need. How much of my other reactant do I need? How can I set up this recipe? How can I mix the ingredients to make the amount of product that I need for whatever I'm trying to do? We generally do chemical reactions because we want to make stuff, and we want to make sure that we create enough. So let's look at a nice chemical example. N2 plus 3H2 gives me 2NH3. These are molecules. The nitrogen is the blue circles and the hydrogen are the white spheres. So the 1 N2, the 3 H2s, and then gives me 2 NH3s. So there should be like a little arrow there and a plus sign right there. Okay, so how many N2 molecules are required for the reaction of 3 H2 molecules? Okay, well, we can see if we kind of just visually inspect this, we can count, this is 3 H2s, and that's going to react with the 1 N2. So we would expect 1. And we can formally treat that by using, again, the coefficients, where we can see the 3 right there becomes the 3 right here, and the 1 right here is there's an implied 1 in front of that. So we're using those coefficients, and we're counting individual molecules, right? Remember, these coefficients come from balancing equations where we were counting atoms inside of molecules. And so we're still in this world of counting. Okay. How many NH3 molecules can be produced from 9 H2 molecules? Well, now we can see that if you had 9 H2 molecules, that's more than the 3 that you start with. But what you're seeing is it's 4 every 3, right? So you take the 9, divide it by the 3. You can see 9 divided by 3 gives you 3. So there are 3 groups of enough hydrogen molecules to do the reaction, and for each of those you will expect to produce exactly 2 ammonias. So 3 times 2 gives you 6. So you can see these relationships, you can use those they come from counting and balance, but those ratios then give you that information. How many moles of NH3 can be produced from the complete reaction of 9 moles? So this is kind of a more practical scale. If you're actually doing this reaction, you would be counting your amount of substances by moles. Remember, mole is kind of the relevant amount of molecules. But we still use the same coefficients. It's 2 moles of NH3 comes from the 2 right there, and the 3 moles of H2 comes from the 3 right there. The one thing you'll note is we just have changed everywhere to moles, which is fine because it just needs to be a counting unit. As long as you're consistent in that you're counting by the same size group. Previously it was all molecules. Now we're just using moles. So, how many moles of CO2 are produced in the reaction of C3H8 with 0.34 moles of O2? We guys want to start by asking, what do we want? And we're told it's how many moles of CO2. Right? We can see CO2 is a product. So what we're really asking is basically, how much product am I going to get from the reaction of an amount of O2? So we can see we're starting with some amount of O2, which is a reactant. So this sort of question is what stoichiometry allows us to do. I have an amount of reactant. How much product will I get out the back end? Right? What do I get out of the back end? And so, those sorts of ideas are really, that sort of a question and idea is what stoichiometry really is going to allow us to do. And we can also note, if we start to look at these, right, I'm relating O2 with CO2. If we tried to use our previous understanding of, chapter 3, Avogadro's number, molecular formula, these are just two different molecules. They don't have the same molar mass. They're not related by molecular formula. So when we want to think how can we relate them, it has to be reaction coefficients. The fact that we are given an explicit reaction for them is also a really good sign that we want to be using these coefficients, that 5 and that 3. And that's going to allow us to relate these different substances in the reaction, reactants and products. So let's go see what that looks like.
Okay, so what we want is how many moles of CO2. So we know in the end we'd be looking for our answer to have units of moles CO2. And they're produced in the reaction of C3H8 with 0.34 moles of O2. So we know that this is basically what we're going to have as our starting point. The fact that it's a reaction of C3H8, that's just telling you that this is the chemical reaction you're working with. So basically it's just telling you combustion of C3H8, you're reacting C3H8 with O2, so it's just a combustion reaction. And so if we take it, we can fill that in, and so we know we would get 0.34 moles of O2. And then, we can plot it out as we want to get out of moles of O2 and go to moles of CO2. Right there. And so when we see this, if we look at like this beginning and exit or end, they're both moles, so they're both counting units, but we're changing what we are counting. This is oxygen molecules, this is carbon dioxide. Right, and those are two different kinds of compounds. And so we would ask, like, how are those two? These are not, there is no generic relationship between oxygen molecules and CO2 molecules. The relationship has to come from the chemical equation. And the relationship then is going to come from these coefficients. Okay, those coefficients that come from balancing, right? The idea is we know that that came from balancing. 5 molecules would react to give you 5 molecules of O2 would give you 3 molecules of CO2. And so what we do is we take that number, so moles of O2 has to come from the 5 that's right there. Moles of CO2 is the 3 that's right there. So we have to pull our reaction coefficients. And so if I want to know for CO2, I just look in the equation, there's a 3 next to CO2, so that goes right there. O2 has a 5 next to it in the balanced equation, so it's 5 moles of O2. Those moles are going to cancel out right there. We'd be left with moles of CO2. Whenever we are trying to relate amounts of two different things that are involved in a chemical reaction, we always use the reaction coefficients. Okay? We always use reaction coefficients. So one of the things we want to think about then is the number that we get. We need to round it. And so we want to look at sig figs. So this has 2 sig figs. These coefficients are going to be exact. So because the coefficients, if you think about it, they come from balancing, and balancing comes from counting. This is 1, 2, 3, 4, 5 O2 molecules, 1, 2, 3 CO2 molecules. So coefficients are always going to be exact. So our answer needs to have 2 sig figs. So we get 0.20 moles of CO2. So what this is telling us is if you react this much oxygen 0.34 moles of oxygen, you will produce 0.20 moles of CO2. That is exactly how much CO2 you're going to produce in that reaction of that much O2, right? So this is kind of this is the primary goal of stoichiometry, that we can relate these different reaction amounts, which is something we generally want to know, right? How much product am I going to make is a common question in chemistry.
Now it's your turn. Participation 615, question 1. Iron ore is refined via reaction with carbon monoxide according to the following reaction. Fe2O3 solid, that's iron ore, plus 3CO gas becomes 2Fe solid and 3CO2 gas. Suppose you have 5 moles of Fe2O3. How many moles of Fe, iron, can you expect to produce from this sample of Fe2O3, which is iron ore? This is the first question for participation 615, due Tuesday, June 15th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, your reaction, Fe2O3 solid plus 3CO gas becomes 2Fe solid plus 3CO2 gas. Suppose you have 5 moles of Fe2O3. How many moles of Fe can you expect to produce from this sample of Fe2O3? All right, so we know previously from dealing with moles and all these conversions, we had 3 primary tools: molecular formula, Avogadro's number, and molar mass. And those all let us relate one substance. So when we were looking at this right here, those tools that we learned in chapter 3, that was describing the amounts of things in one substance. How many atoms in this molecule? How many grams in these moles? How many atoms in these moles, right? All of those sorts of relationships. And now reaction coefficients slots in within the same idea, but it's going to be a slightly different tool. One, it's only related to specific chemical reactions. And using these reaction coefficients allows us to convert between different substances in the reaction. So you can completely change what you're looking at. Silver to gold, to if they're in a reaction, doesn't matter. You can entirely change the substance, and reaction coefficients are the only way to do that. If you're looking to relate 2 different substances that aren't in the same molecular formula, aren't in any other way like that, you have to use your reaction coefficients. This is where stoichiometry comes in. All right, first video down. Already have a question for participation 615. That one's due Tuesday. Want to find all of the questions across this set. Module 5 homework is due Wednesday. That's June 16th at 11:55 p.m. over on Sapling. That'll cover both sides of the assignment, both sets of videos. And then the reactions of copper lab is going to feature a lot of information. It features a lot of stoichiometry ideas in terms of doing the analysis itself, a lot of stuff from this set of videos. So it'll certainly hopefully make a lot more sense once you've watched these videos. But otherwise, we're just getting started. If you have any questions about any of this content, you still want to talk about exam 1, anything like that, do not hesitate to reach out. Email me, come to office hours, give me a call, text me, put a question in the discussion boards. Happy to get those questions answered. Otherwise, I am excited to continue on with this set of videos. I'll see you in the next one.